you very much, fellow Kenyans. I'm Comrade Babu Owino, a Member of Parliament, Embakasi East constituency, and your favorite son. Today, we'll be handling physics as physics. It's okay? Oh, sorry. Sorry, there was a problem with the reception. Today, we'll be handling physics. And in physics, we'll be handling a topic called electromagnetic induction. And physics will be handled by Mr. Mbuguswa, who is a very experienced teacher, a teacher who's really made engineers in this nation. And the engineers, we shall also bring them at some point with the time, at least to testify what this teacher has done to their lives. And I'm also proud to say that this is a teacher who's also taught my wife, Frida Mudhoni, a very beautiful lady and a very intelligent lady. And thank you very much for inducing intelligence in my wife's mind. And for that reason, I want to take this opportunity to welcome you, Mr. Mbuguswa, as you'll be handling electromagnetic induction. And class will also be giving airtime bundles, so kindly comment with your numbers. Lastly, we have our EduCare Foundation. The EduCare Foundation will be handling, we are working on an application which is almost ready, that will be handling all the content that you need as a student. One thing that I only ask the parents and the students is just to trust this team with your child, trust this team just with yourself, and we will change your life as time passes by. We will ensure that those who are at worst position become good. Those who are good will be better. And those who are better will be best, if not perfect. Thank you very much. Karibu mwalimu.
Thank you.
Karibu.
Thank you, sir. Yeah, good afternoon, students. Yeah, my name is Martin Bunguswa. I'm a teacher of physics and chemistry. Today, I want to take you through a topic called electromagnetic induction, which is taught in Form 4. We have the objectives of the specific objectives of the topic, which you can see on my screen. Now, in the year 1791, a scientist by the name Hans Christian Ørsted discovered that it is possible to make a magnet using electricity. Now, thereafter, scientists were posed with the problem of how to reverse the effect and produce electricity from a magnet. In the year 1831, a scientist by the name Michael Faraday started these experiments which demonstrated the principle of electromagnetic induction. And this was based on a series of experiments that were done to that effect. One of these experiments was set up like this. We take a U-shaped magnet and a straight conductor which is connected to a very sensitive galvanometer. He moved the magnet parallel to the wire parallel to the magnetic field, and he noted that there was no deflection. He moved the conductor perpendicular to the magnetic field and noted that there was a momentary deflection. And he realized that the deflection should be due to a current that has been induced in the conductor. And this current he referred to as induced current, which was due to an EMF that had been induced in the same conductor. It was also discovered that if the conductor is held stationary in the magnetic field, there was no such a deflection. Therefore, it was concluded that for an EMF to be induced in a wire, there must be a change in the magnetic flux. Remember, between the two poles of a magnet, there is a magnetic field. And a buildup of the magnetic field is called a flux. And when that flux changes, an EMF is induced. And that EMF is what leads to an induced current. So that experiment can also be carried out by keeping the conductor stationary, but we move the magnet. We move the magnet in or outside the magnetic field. So in this experiment, it is set up as you can see there. There is a cardboard, and then wound on it is an insulated copper wire whose ends are connected to a very sensitive galvanometer. It's observed that if the magnet is held stationary inside the coil, there is no deflection in the galvanometer. If the magnet is moved towards the coil with a particular pole of the magnet, there will be a momentary deflection. When you talk about momentary deflection, it means the current induced is not so much. It's just for a moment, and then it returns back to zero. But the direction in which the galvanometer deflects will also depend on which pole of the magnet is being used to induce the current. So if you use the south pole, the deflection is different from if you used the north pole. Therefore, at that point, we can conclude that an EMF is induced in a conductor whenever there is a change in magnetic flux. But if the flux is not changing, no EMF is induced. And at that point, the scientist by the name Faraday came up with a first law. And the law states that an EMF is induced whenever there is a change in magnetic flux linked with the coil. And the change in magnetic flux is brought about by either keeping the magnetic field stationary and move the conductor, or keep the conductor stationary and move the magnet. That is what we call Faraday's first law of electromagnetic induction. Now, what factors affect the size of this induced EMF? So more experiments were done to investigate the factors that affect the magnitude of induced EMF. And in the experiments, we need an insulated copper wire, a cardboard tube, a weak magnet, a strong magnet, and a sensitive galvanometer, and a piece of soft iron. The reason why we are using a strong and a weak magnet is to establish how the strength of the magnetism affects the size of induced EMF. And that experiment is carried out using the setup that you can see. So we wound the insulated wire on top of the cardboard, and then again we connect to a very sensitive galvanometer. We are using a galvanometer in this experiment because a galvanometer is used to show the direction of current. We did not use an ammeter because an ammeter only measures the amount. We did not use a voltmeter because a voltmeter measures what we call potential difference. Now in this experiment, we start by looking at how the number of turns of the coil affect the size of induced EMF. So we still move the magnet. The magnet, when it's kept stationary, we have realized that there will be no induced EMF. So we move the magnet towards the solenoid with a particular number of turns. With a particular number of turns and not the amount of deflection. So it is observed that when the number of turns of the coil in that setup increases, with the same strength of the magnetic field, the amount of deflection is greater. We also do the same thing, but now we keep the number of turns the same, but we increase the speed at which the magnet is moving towards the solenoid, which can also be repeated using the earlier experiments. And it's noted that the faster you move the magnet towards the end of the solenoid, the more the deflection. And that size, the rate of motion is called changing the magnetic flux, the rate of change of magnetic flux. We can also keep the speed of motion the same, but now introduce a stronger magnet towards the end of the solenoid. It will be observed that if the magnetic field is more stronger, then there will be more induced current. Then we can also keep the magnet the same, but inside the coil, we place a piece of iron rod. We are strictly using an iron rod because you remember in Form 2, when you learned about the magnetic effect of electric current, you learned about the effect of soft iron. Soft iron is easily magnetized and also easily demagnetized. Therefore, if we introduce soft iron inside the solenoid and then move the magnet towards, it is also observed that the deflection is a bit more greater. So out of that, we can now summarize the factors that affect the size of induced current. One of the factors is the speed with which the magnet is plunged into the coil. We can say that the size of induced EMF is directly proportional to the rate of change of magnetic flux. Number two is the presence of soft iron armature in the coil. The presence of soft iron concentrates that magnetic field, and that increases the size of the induced EMF. The third factor is the strength of the magnetic field. The stronger the magnetic field, the more the flux, and the larger the amount of EMF induced. And the last factor is the number of turns in the coil. The more the number of turns, the stronger, the greater the induced EMF. There is also now Faraday's second law of electromagnetic induction. So the second law of electromagnetic induction is actually a summary of the factors that affect the size of induced EMF. It states that the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linked with the circuit. Now, sometimes the two Faraday laws are combined together, and therefore, at the moment, if we are asked to state the Faraday's law, you can give the combined law, which states that whenever there is a change in magnetic flux linked with a circuit, an EMF is induced, whose magnitude is directly proportional to the rate of change of the flux linked with the circuit. Remember, Faraday's law refers to induced EMF and not induced current. EMF can still be induced even if the circuit is open, but current cannot flow in an open circuit. So when you are stating the Faraday's law, even if you are to state as the amount, whenever there is a change in magnetic flux, an EMF is induced or a current is induced, it is still acceptable. But it is important to note that we refer to induced EMF. And whenever EMF is induced, current is also induced. Now that is about the Faraday's law. We have been able to see that whenever magnetic flux changes, an EMF is induced. But when the flux is not changing, there is no EMF. We have also looked at what factors affect the size of the induced EMF. But then, what about the direction? In which direction is it flowing? So Faraday had now to consult with other scientists. There were two of them. One is Lenz, and the other one is Fleming's. They worked on the direction that now we have generated the EMF. In which direction is going to flow? So Lenz worked on current in a coil, and then Fleming's worked on induced current in a straight conductor. Now Lenz's law can be applied together with the Fleming's right hand in predicting the direction of induced EMF. Let's start with the Lenz's law. Now, this is after so many experiments and so many investigations in that work of electromagnetism. And Lenz law states that the direction of induced EMF is such as to oppose the change causing it. The direction of induced EMF is such as to oppose the change causing it. Lenz, I think, worked closely with another scientist in chemistry known as Le Chatelier, when he also worked on what we call the stress management in science. That whenever stress is applied to a system which is in a dynamic equilibrium, the system will always try to oppose the change or whatever brought the stress. So we can also link up with what we call the Lenz, that current will be induced, but the direction in which it will flow is such as to oppose the change. Just like you go towards the door and then it's closed. When you move out of the door, it is opened. So work must be done, therefore, to open that door. and the work done becomes converted to electrical energy. So let us see how we can apply the Lenz's law in predicting the direction of induced current. Here what you can see there is the right hand grip, which can be illustrated in that particular figure. And the right hand grip, which we taught you in Form 2, states that if we imagine that you are holding something like a solenoid in your right hand, with the fingers pointing in the direction of the current, then the thumb will always point in the direction of the north. So you can hold it like this if the current is going down. You can hold it like this if the current is moving in this direction. You need that particular rule for you to be able to appreciate what Lenz was referring to as current will flow in a direction to oppose the change. Let us see this particular first diagram. We are moving the north pole of a magnet. Remember, we must move it because if it's not moving, then EMF will not be induced. We are moving the north pole of the magnet towards the end of a solenoid. It is observed practically that the deflection of the galvanometer is towards the left, or the current will be moving clockwise. Therefore, how can you be able to use this to explain the Lenz's law? So the deflection of the galvanometer to the left shows that the current is flowing clockwise as shown in that particular coil. Now assume that you are now holding that particular solenoid in your right hand with the fingers pointing the current direction. Then you notice that your thumb is pointing towards the left. Now Lenz says that if you move the north pole of the magnet towards the end of the solenoid, the current is going to flow in a direction as to oppose. And in this case, it is going to prevent the north from moving in. So the question is, how should you hold that solenoid so that the left becomes the north? And the only way you'll hold it is this way, with your hands pointing up. And if you do that, then that one automatically gives you the direction of the induced current, and that explains why it is moving in that particular direction. Let's look at the second setup. Suppose now I move the north away from the solenoid. The current will be induced to flow in such a direction as to create a south pole at that end that will prevent the north from moving away. So how should we then hold this solenoid for that end to become the south pole? You hold it like this, in that particular direction. And if it's held this way, then you notice that the current is going to flow to the right. So what we can therefore conclude from this is, the direction of the induced current will all depend on which pole you are using to induce the current. If you use the north, the direction of flow of current will be opposite to when you use the south. But again, remember, there will be no flow of current if the magnet is held stationary inside the solenoid. That is what we call the Lenz's law, that the direction of induced EMF is such as to oppose the change causing it. And the easiest way to understand the Lenz's law is apply the right hand grip. Just imagine that the particular end is to become a south pole. How should you hold it to become a south pole? I'll hold it like this. I want that particular end to become the north. How should I hold it? I hold it like this. If I hold this one to become the north, then that is the flow of current. If I hold it this way, this one becomes the south, then this is the flow of current. But if you stop moving the magnet, there will be no deflection in the galvanometer. The second rule is called the Fleming's right hand, which is also called the dynamo rule. Now, whereas we can use the right hand grip rule to predict the length, we now use the Fleming's right hand rule in case the conductor is straight. And the Fleming's right hand rule states that if the first three fingers of the right hand are placed mutually perpendicular to each other, with the first finger pointing the direction of the magnetic field, which in this case points from north to south. The thumb points the direction of the motion of the conductor. Then the second finger is going to give you the direction of induced current. And it can be shown in the second diagram down here. That is now what we call the straight conductor. Where you are seated, sit in such a manner that your first finger is pointing from north towards the south. You are allowed to move. Then let the second finger now point that direction of the current. In this case, there are two ways we can ask you this question. Either we give you the direction of induced current, we ask you to tell us the direction in which the wire was moving. Or we give you the direction in which the wire is moving, but we ask you the direction of the induced current. Now, the diagram that we have here, we have already given you the direction of induced current. So we want you to give us the direction of motion of the wire. So the first finger points from north-south. The second finger will point the direction of the current, and the thumb will point the direction of motion. In this case, there are only two directions. Either you are moving the wire up or you are moving the wire down. You cannot confuse. It can't be sideways, because if you move it sideways, there will be no EMF. It cannot be up or down. Sometimes it's not very easy for you, the students, to know whether you're going to use the left hand or the right hand. In Form 2, we taught you about the left hand rule, which was predicting the direction of motion. But now in Form 4, we are teaching you the right hand rule. So it is a matter of practice, because we realize most of us cannot be able to synchronize the motion of the hand so that it can show up or down. And if you want to know the correct position of the hand, we shall even ask you to go back to the internet and check on how those hands are supposed to be placed. Now that's about the direction of induced EMF. Now we move on to what we call mutual induction. Now we have generated EMF. We have known the direction in which it is moving. We have been able to predict the direction, and we know how to increase the size. Now, what is mutual induction? Mutual induction occurs when a change of current in one coil induces a current in another coil placed close to it. You are inducing something in a person. The two people must be together. When a change of current in one coil induces current in another coil placed close to it. So that means that you need two circuits. One of the circuits is connected to the source of EMF, which is subjected to a change. But the second coil is connected to a sensitive galvanometer with no source of EMF. So that first coil is called the primary. And the next one is called the secondary coil. So we are going to see how we can induce current in the secondary coil. Now, this setup can be used to demonstrate what we call mutual induction. When the switch in the primary circuit is closed, and remember, the two solenoids are wound on a piece of wood. Remember, in electromagnetic induction, we don't use a metal. We use something that is an insulator, and you only put a conductor on top of it. So you take a piece of wood, and then you wound two turns of coils in opposite directions, so that you have the primary with the battery and the secondary without the battery. It is observed that when the switch is closed in the first circuit, or even the second circuit, the two represent the same thing. When the switch is closed, current in the primary coil increases from 0 to maximum within a very short time. That increase of the current is also changing the magnetic flux from 0 to maximum. Therefore, the magnetic flux that has been induced in the primary will link up with the magnetic flux in the secondary, and therefore the galvanometer is going to register what we call a momentary deflection in one direction, and returns back to 0 when the switch remains closed. How do we vary the current in the circuit? The amount of current in the circuit can be varied by using a variable resistor which has been attached in that circuit. You can use it to regulate the current from 0 to maximum. Now, when you open the switch, again it is observed that there is going to be a momentary deflection in the galvanometer attached to the secondary coil, but again, it returns back to 0 when the switch remains closed. Now, clearly it shows that a change of EMF in the primary circuit is inducing an EMF in the secondary circuit, and that explains why there is a deflection in the secondary coil. But the induced EMF in the secondary coil is much higher when the current in the primary is switched off than when it is switched on. The reason is because the current in the circuit takes much shorter time to die off than to build up. So that phenomena is what is referred to as mutual induction. Now, how do we increase the size of EMF in the secondary? One is by having more turns in the secondary coil, as explained earlier. Two, by winding the primary and the secondary coil on a soft iron. We can use a soft iron rod, or we can use a soft iron ring, as you can see in the setup down there. The role of the soft iron ring is to concentrate the magnetic flux because it is easily magnetized and also easily demagnetized. Number 3 is winding both the primary and the secondary coils on soft iron. We can use a soft iron rod, like in the first diagram up there, or we can use, this is now called, we can use the soft iron rod. In this diagram, that rod can be made of soft iron. Instead of having a piece of wood with wires wound around it, we can just use a soft iron rod. If not that, we can use a soft iron ring. It is called the Faraday's iron ring, which is just below that first diagram. So those are the 3 ways of increasing the size of induced EMF in the secondary coil. And that process is called mutual induction, where you can induce EMF in the secondary coil by simply using some current in the primary coil. What are the applications of electromagnetic induction? Now, the discovery of the whole of this topic was to be made useful in many of the appliances that you could be using even in our homes or even outside there. So where is it applied? The first application of electromagnetic induction is in the working of a transformer. Now, a transformer works on the basis of what we call mutual induction. I believe you've been seeing transformers out there. We also have small transformers which are found inside the radios. But you can only open the inside of the radio for you to see a transformer. We also have transformers in televisions. We have transformer in many of these electrical appliances. But out there, there is a transformer that looks like that. Whenever you see such a device out there in the field, it is called a transformer. And I want you to know that it is not storing water, it is storing electricity. So what is a transformer really? A transformer is a device that is used to change the magnitude of electrical energy, either from a lower value to a higher value or from a higher value to a lower value. And the working of a transformer relies on what we call mutual induction. In the diagram of the transformer down here, this is just the way we represent a transformer. There's a model. This is called a model of a transformer. It is made up of 2 coils wound on soft iron. Where the electricity gets in is called the primary coil, and where the electricity gets out is called the secondary coil, and it's been wound on soft iron. We have been able to explain that one way of increasing the size of EMF induced in the secondary is by use of soft iron, and that is exactly why we're using soft iron and not a wooden rod. And then They are wires. These wires wound on the ends of the transformer are insulated. And you discover that the inside, if you look at that model of the transformer, the inside is just hollow. That means that the two wires, the primary and the secondary, are not directly connected, but they are connected mutually. What gets in is called AC. AC stands for alternating current. And what gets out is also called alternating current. There are two types of electric currents. There is alternating current and there is direct current. The main difference between the two is that alternating current is sinusoidal. It flows in cycles. The one we are using to light our homes is called alternating current. But direct current can only flow in one direction, like the current generated by a dry cell or a battery is called direct current. Now, mains electricity, which is a topic that we teach you later, deals with the generation of alternating current, where we tell you what are the advantages of generating AC. While the Kenya Power supply AC, the people generating electricity generate AC. The reason is because AC can easily be stepped up or down using a transformer whose working relies on mutual induction. And also, AC can easily be changed or be converted to DC by using something called a rectifier, which is a series of so many diodes. Now that I've mentioned something that AC can be stepped up or down, we want you to know that there are two types of transformers. There is what we call a step-up transformer, and there is what we call a step-down transformer. So because we are not teaching you the practical transformer, there is a way we can now use the sketches to tell you which one is a step-up and which one is a step-down. A step-up transformer increases the voltage from very low to very high. Like mains electricity, when it's being generated, for example, at Olkaria, it is 1,000 or so volts. But for the purpose of transmission, it is stepped up to more thousands now. We shall be teaching you why we need to step up the voltage for transmission. Therefore, if it increases the voltage from a low value to a higher value, it is called a step-up transformer. So let's start with the step-down transformer. Step-down transformer now reduces the voltage. It does not reduce energy, it only reduces the voltage. Now, once the electricity has reached the home, we only need around 240 volts. And maybe what is coming in is 12,000 volts. It must be stepped down to 240 for it to be used in the appliances that we use in the home. So we use what we call a step-down transformer. So how do you tell the difference between a step-up and a step-down? If it is mounted up there, you cannot easily tell. You cannot tell by looking at the size of the transformer, but you look at what you call the turns. If the number of turns in the secondary are fewer than the number of turns in the primary, then it is called a step-down transformer. Those are the two ways we can represent the step-down transformer. We have the primary with many turns, the secondary with fewer turns. That is also how we can represent the turns. We just show the coils. There are more in the primary and fewer in the secondary. That is called the step-down. And in mutual induction, we were able to learn that the amount of voltage induced in the secondary also depends on the number of turns. If I increase the number of turns in the secondary, I also increase the voltage. Therefore, we can comfortably say that the turns and voltage are proportional to each other. So if you take the voltage in the secondary, you divide by the voltage in the primary, it gives you what you call the turns ratio. And in terms of turns, we can also say number of turns in the secondary over number of turns in the primary is the turns ratio. And because the turns ratio is the same, then mathematically we can say voltage in the secondary divided by voltage in the primary is the same as number of turns in the secondary over the number of turns in the primary. Now for the step-up transformer, it is the opposite now. The number of turns in the secondary will be much more than the number of turns in the primary. So step-up transformers will be used, for example, to supply electricity to an industry. Step-down transformer may be used to supply electricity to a home. Step-down transformer may be used to supply electricity to a radio or such electrical apparatus. So it is the number of turns, not the way you place the transformer. So that is now the difference between a step-up and a step-down. Step-up reduces the voltage. Step-up increases the voltage. Now, based on what you call the turns ratio, this one is what you call a mathematical expression that relates to transformers. That the voltage in the secondary over the voltage of the primary must be equal to the number of turns in the secondary over the number of turns in the primary. Just a correction in that formula. You change the denominator to read number of turns, number of primary turns, because it's proportional to each other. This is what you call the turns rule. And mathematically, that is how it is represented. Vs over Vp is equal to Ns over Np. In Form 3, we had learned the topic on current electricity. And under the current electricity, we were able to state the Ohm's law, that current through a conductor is directly proportional to the applied PD, provided temperature and other physical conditions are kept constant. And from Ohm's law, we were able to write that V is equal to IR. Then you also recall the topic on the heating effect of an electric current when we taught you about electric power. We said that electric power is given by voltage times current. So P is equal to VI. So therefore it's important for us also to be able to calculate what we call the power input in a transformer. So power input in a transformer will be given by voltage in the primary times current in the primary. Then power output will be given by voltage in the secondary times current in the secondary. Now a transformer is like a machine. We are supposed to quote its performance in terms of efficiency. And the efficiency of a transformer will be measured as a percentage, just like any other machine, wheel and axle and the like. And efficiency is given by taking the power output, you divide by the power input, expressed as a percentage. If now write the expression for efficiency, it becomes Vs Is over Vp Ip times 100 gives us what we call efficiency. So that expression can also now be written. The turns ratio rule can also be written as Vp Ip is equal to Vs Is, assuming that the transformer is ideal. Ideal means it has a percentage efficiency of 100. So we have now two expressions here for the turns ratio rule. Vs over Vp is equal to Ns over Np. And you now have Vp Ip is equal to Vs Is. Can you be able now to rewrite and put all of them together so that we are able to get an expression that has current, turns, and voltage? It is possible. And it is written as Vs over Vp is equal to Ns over Np and is equal to Ip over Is. It's a very simple expression to remember. What's important for you to know that voltage is proportional to the number of turns. And this is what we call the turns ratio rule. And it happens to be the only calculation that we can use when working with transformer in this particular topic. I'll show you an example of how it is done, and you'll accept that the examples of this topic are so easy. In fact, you don't need to think. A transformer is to be used to provide 240 volt ceiling bulb from AC supply of 240. So that means 240 is the voltage in the primary. 24 is the voltage in the secondary. You write like that. Find the number of turns in the secondary coil if the primary coil has 100 turns. So now you write Ns, we don't know, but Np it is given. Now start by writing your formula. Vs over Vp is equal to Ns over Np. Then do the substitution. 24 over 240 is equal to NS over 1,000. And when you do some numerical division, you get 24 times 1,000 over 240, and that one gives you 100 tons. The example I've selected is one of the hardest. So you can imagine how the easiest look like. And that is how it can be. So any other example I'll give you look exactly like that. So I don't need to give you 20 examples. Just rely on that and it will be enough. Maybe the only thing I could have asked you is to calculate the percentage. But now I have given you more other examples. If you follow, you can be able to realize how easy it is to do the calculation. That is called an ideal transformer. But practically, the efficiency of a transformer is never 100. So I want to know why. Why is the efficiency of a transformer, practical transformer, not 100? We need to look at what are the causes of energy loss in a transformer. And against each, we want to know how it can be minimized. There are 4 main causes. There could be others. The other causes, because you can vandalize a transformer, you have reduced the efficiency. But you're not talking about those ones. Number 1 is called flux leakage. I want you to know there's a difference between flux leakage and flux linkage. If the flux is not linked properly, it leaks. Now, during mutual induction, the primary magnetic flux is supposed to link with the secondary. But because of the design of the transformer, sometimes we find that the number of turns in the primary are not well linked to the ones in the secondary. So some flux leaks. So the flux leakage is due to insufficient flux linkage. And in the practical transformer, this has been minimized by winding the secondary on top of the primary. So we have now the primary turns, we have the secondary, but both of them are wound together, as you can see in that particular setup. We have the primary coil on one side, the secondary coil down there. That is now the new design of the transformers that practically we are using. That is meant to ensure there is maximum flux linkage, so that there is less flux to leak. The second cause of power loss is called resistance of the coils. We are using the insulated copper wires around the transformer. Sometimes these copper wires offer a lot of resistance. And the way to minimize, now resistance produces heat, because remember, resistance is blocking something from moving. And when something is blocked from moving, it is likely to resist. And the way electricity resists is that it becomes heat. And therefore, this has been prevented by use of thick copper wires. So the thick copper wires help to reduce the heating effect due to the resistance. When you did the factors affecting resistance of a conductor in Form 3, we said one of them was the length of the conductor, another one is the cross-sectional area, another one is the temperature, and another one is called resistivity. When put in a formula, we have R is rho L over A. So the thicker the wire, the lower the resistance, and therefore the less the amount of energy to be lost. The third cause of power loss is called eddy currents in the core. Eddy currents have associated fluxes that tend to oppose the flux change in the primary. This reduces the power transfer to the secondary. Remember, flux, eddy currents, we are supposed to be taught under what we call self-induction, which we no longer teach you. But I want you to know that when the current is passing through a solenoid, when the current is passing through a conductor, according to Lenz's law, it is going to induce some EMF that will tend to oppose it from flowing. And that opposition is what we call eddy currents. The only eddies you've learned is maybe in the topic called the Bernoulli's principle, when we looked at the eddies and how they cause turbulence. Now, these eddy currents are reduced by use of what we call laminations. Laminations are thin sheets of insulated iron which are placed together. Now, those insulations increases the cross-sectional area, And when the cross-sectional area increases, the resistance also reduces, and therefore the eddies are able to flow with less amount of resistance. That's how we minimize eddy currents. And the last cause of power loss in a transformer is called hysteresis. Remember, the soft iron is used in the transformers to increase the size of induced EMF in the secondary. Now, when we pass the current through the primary of the transformer, the iron core becomes magnetized. Then when we are reversing the magnetic field, it becomes demagnetized. So sometimes there is what you call the reluctance of the dipoles in the domains to realign, to face in a particular direction. Because like you are being told, go this side, then come back. Go that side, come back. In the middle, some people lose orientation. And that is what you call the hysteresis. And this hysteresis is minimized by use of soft iron. Most of the practical transformers that we get in the market have what we call a soft iron core, which minimizes the power loss due to hysteresis. So there are 4 of them. We've said there's hysteresis loss, the eddy currents, resistance, and what you call the copper, that is the copper losses. So you need to know the cause of power loss and how it is minimized. Then you are saying that a transformer used in power stations for long transmission generates a lot of heat, and they are therefore cooled by oil, which does not easily evaporate. So the transformers that we have in the homes don't have oil. They are cooled by air. But the practical transformers in the market, they use oil. And that oil does not easily evaporate because it has what you call a very high specific heat capacity. Those are the ones that are used. And the oil used in the transformers is very expensive. No wonder some people have under the transformer to steal the oil. And don't try it because you know the effects that will be involved with the AC. The next application of electromagnetic induction is in the working of what you call the generators. Those generators that you see in the market, their working relies on what you call electromagnetic induction. Do not confuse a generator and a battery. A battery is not a generator. A generator is used to convert mechanical energy into electrical energy. We can say it is a transducer. A transducer is a device which converts energy from one form to another. So this one converts mechanical energy to electrical energy by electromagnetic induction. Now we have 2 types of generators. There is what we call the AC generator and the DC generator. AC generator generates alternating current, but DC generator generates direct current. An example of a simple AC generator that you may have come across is the alternator in the vehicle. In the vehicle, there is a battery and there is what you call the alternator. So the alternator is an example of an AC generator. Another one is a dynamo that we may find even in bicycles. That is also an example of an AC generator. Essentially, the AC and the DC generator look the same, but I want us to look at the structural differences between the two. This is the structure of an AC generator. It has what we call the slip rings, and it also has what we call the carbon brushes. And then it is also made up of a magnet which has curved poles, as you can see. Then it has an armature which is rectangular. The armature is made to rotate inside the magnetic field. And from the previous discussion, we've been able to see that whenever a conductor is made to move in such a way that it changes the magnetic flux, current is induced. And that is how it works. The only difference now, how does this electricity get out? We now have what we call the slip rings. So the slip rings now change the direction of the current. Now the poles of the magnet you can see are curved. The reason why they are curved is in order to produce what we call a radio magnetic field. Radio means something along a radius. so that when the coil is rotating in that magnetic field, it cuts it uniformly. It cuts it uniformly and generates an electric current. So the main two important features, we have the carbon brushes and the slip rings. The brushes are made of graphite. If you learned in chemistry uses of graphite, you are taught that is used to make brushes in dynamos and generators. Now, what is the function? Why is the brush made from graphite? One is because graphite is a good conductor of electricity. In fact, it's the only non-metal which is a good conductor of electricity. And two, graphite is slippery. And because it's slippery, it can therefore act as a lubricant. Now, when the coil rotates, remember when the coil is stationary in the magnetic field, there is no EMF induced. When the coil rotates, it is cutting the magnetic field. And remember, the size of the current induced increases with increase of the angle. So when it is like that, it is actually perpendicular to the magnetic field. It's cutting the magnetic field at 90 degrees. When you move it along the axis of rotation, the current is going to be induced because it's cutting the magnetic flux. But the direction of that current is governed by what you call the Fleming's right hand, which we have discussed. You can be able to read through and understand how the coil is moving, but it is cutting the magnetic flux. Look at the position of the slip rings. There is one at Y, there is also another one at X. At some point, it gets in through X and gets out. When the longer wire is touching at X or 2. At some other point, the current gets in through Y. And you can see it's getting through X, goes up, Y, then comes down like that. That current that we get outside is called alternating current. And we shall ask you in the exam to sketch a graph to show how the voltage varies with time when the coil is rotating. And the graph is as shown below. This is now the output as displayed from CRO. We connect something called a CRO. CRO stands for cathode ray oscilloscope, where cathode ray oscilloscope simply means plotting a graph using cathode rays. And cathode rays is a stream of negative charge electrons produced through a process called thermionic emission from a very hot cathode. That is the shape of the graph that we get, depending on the position at which the coil is starting. Like this graph that you find is when the coil is starting perpendicular. When it's perpendicular, no, it's not perpendicular, it's in the vertical position. We start from 0, it goes to maximum when it's 90, then it reverses at 180, goes again in the opposite. That's why it's called alternating current. Whether it is going up or down, the magnitude is actually the same. That is called an AC generator. Then a DC generator works exactly the same. But now the difference here is that a DC generator has what we call a split ring commutator. You know the meaning of to commute. To commute, you go and come. So this is called a commutator. Because unlike now the AC generator, the slip rings are fixed. Let's look at the structure of a DC generator. In the DC generator, we have what we call a ring that has been split. It's called a split ring commutator. We also have the carbon brushes. The brushes have exactly the same role as in the other generator. The only difference here is that the commutator will be moving. The brushes are kept stationary, but the commutator is moving. At one point, X is where it is, and Y is where it is. When this coil rotates, this ring that was on side X goes to Y, and the one that is at Y comes to X. So essentially, the brush on the right-hand side remains positive, and the brush on the left-hand side remains negative at all positions of the coil. But again, remember, there is no EMF induced if that coil is in the vertical position. So if we sketch a graph to show how the voltage varies with time for a DC generator, that is how it looks like. When we teach you a topic called electronics, we shall mention that it is not a smooth output. But the smooth output can be achieved by using a capacitor. That one will come later on. But now this is now the graph. Now, what is it that is important for us, the student, to know on the two generators? One, we shall draw for you the generator in the exam. We ask you to name the parts. And the part is either the split ring commutator and the brush. The other one is the slip ring and the brush. Two, we are going to ask you to sketch a graph to show how the output varies with the time for the two generators. So for the AC generator, there is a way to look like and the DC to look like. But for both generators, how do we increase the size of induced EMF? We can increase the size of induced EMF by either, one, increasing the speed of rotation of a coil, increasing the number of turns of the coil, increasing the strength of a magnet, and also winding the coil on laminated core. A bicycle dynamo is an example of an AC generator. Wakikuuliza in the exam, how do you increase the brightness of the bulb in a bicycle? You cannot say that you use a stronger magnet. You cannot stop the bicycle, go buy a magnet, make it stronger. In this case, you only cycle faster. So when you cycle faster, you are increasing the rate of change of magnetic flux. The second last application of electromagnetic induction is the working of a microphone. A microphone is not the same as a loudspeaker. Both of them are called transducers. Microphone converts sound energy to electrical energy. But the loudspeaker converts electrical energy to sound energy. You'll have to use a microphone with a loudspeaker somewhere, but they work independently. But the structural features of the microphone and the transformer are exactly the same. So what you can see on the diagram here is the features of what you call a microphone. I guess everyone has ever seen a microphone. When you go to church, they're using a microphone. You go for rallies, whatever that thing they're holding is usually a microphone. It may not look like this. This is the inside of a microphone. So which are the features? It has what we call a coil, which is wound on a pot magnet. It's called a pot magnet because it's very small. It looks like a pot. Then there is a diaphragm, which is made from paper, so that it's flexible to move. How does it work? When you speak over the microphone, the sound waves from the source set the diaphragm in vibration, which in turn causes the coil to move in and out of the magnetic field. Remember, that is a pot magnet with a north, south, and a north. So when you speak, the sound waves make the coil to move in and out. That motion in and out causes a change in magnetic flux. And whenever magnetic flux changes, EMF is induced. And that EMF induced is very little. It must go through the amplifier, and then it is fed to the loudspeaker in order to be reproduced. It has already worked like that. It's very simple. So the whole concept here is the change in magnetic flux that produces a current. And the current is very, very small. But for this microphone to work, of course, you must power it. And the last application is called the induction coil. The induction coil is used to ignite petrol-air mixture in a car engine. Remember, we teach you about the car, but at different stages in physics. We taught you about the working of a carburetor when you're doing the fluid flow. We are teaching you about the induction coil when you're teaching you electromagnetic induction. We are teaching you many other parts of the vehicle. So at the end of the 4 years, it is not all about passing the exam, but can you be able to recollect everything and make your own vehicle? Now, this is called an induction coil, and it looks like that. It's a very small part of the vehicle. If you look at the features of the induction coil, it has soft iron wires around which there are so many turns of the coil, which is called the primary. And then attached to it again, there are other wires which are wound on top. Now, the reason why we want the secondary on top of the primary is to minimize flux leakage. And then on the other side, there is now the battery, there is the key, There is the capacitor, there is the platinum contacts, and then up there we have the spark plugs. So in the vehicle kuna mahali inawekwa plugs. Sasa plugs is where now the spark is being produced. And when the spark is produced, inaingia inakutana na petrol vapor. We don't burn petrol as petrol, it's burned as vapor. And when it is ignited, depending on its octane rating, it expands and then it explodes. That explosion makes the pistons to start moving, and the vehicle, the engine is on. But if the pistons don't move, then we say it has knocked. So how does this thing work? When you close the key, when the switch is closed, the soft iron rod is magnetized due to the current on the primary coil and attracts the soft iron armature, which you can see there. When the armature is attracted, it opens the contact and cuts off the current. That reduces the magnetic field to zero. This in turn induces a large EMF in the secondary coil by mutual induction. The spring pulls the armature back to make the contact again, and the process repeats itself. By the way, the induction coil just works like an electric bell. There is make and break, make and break. During make, EMF flows. When there's break, the EMF dies. So we are changing the magnetic field. And that change in magnetic flux induces an EMF in the secondary. Because the secondary has more turns than the primary, a larger EMF is induced, which now flows through to the spark plugs. And because of the point action, a spark is generated. And that spark generated is the one that ignites the petrol. Air mixture, and it stops there. So that is the whole topic of electromagnetic induction, in a nutshell. So next time we meet, we shall be doing revision on electromagnetic induction so that you get to know how are the questions actually tested in the exam. Yes.
Thank you very much, Mwalimu. Thank you very much, Mr. Bonguswa. Asante sana, Mungu akubariki, and I hope that our students really has been induced, knowledge has been induced in your mind, and the coils in the brain has really been magnetized by the knowledge that has been dispensed by Mr. Martin. May God bless you all, class. And kindly, class, next time we'll also will communicate the lesson that will be. I want you to continue staying tuned as we change the lives of our students, those students who are staying in the slums, those students who are staying in the villages. Ensure that I change your lives for the better. Ensure that your mom who is in the slums with you, your dad who is doing a job that is the Juakali in the Juakali industry sector, we will ensure that we change their lives through changing you. By changing you, you will change the lives of these parents. By changing you, you will change the lives of your other siblings. Thank you and God bless you, and I hope you enjoyed. Tibim, asanteni sana.